Okay, so I want you to visualize something for me. Picture the history of the universe.
The standard image.
The standard image, the one you see in every textbook. It looks like an ice cream cone.
Mm-hmm.
You've got this wide, expanding top. That's us right now. And as you go back in time, the cone gets narrower and narrower until
It hits a single sharp point at the bottom.
the singularity. It's the ultimate dead end.
Right. It's where everything we know about physics just breaks.
And the story we've all been told is that everything, space, time, all of it, burst out of that 13.8 billion years ago. But here's the question, the one that always gets you a funny look.
The forbidden question.
What happened before the Big Bang?
For decades, you just weren't supposed to ask that.
Hmm.
The scientific community's answer was basically, stop asking.
I remember Stephen Hawking's big analogy for this. He said, it's like asking.
What is north of the North Pole?
Exactly. The idea was that time itself began at the Big Bang, so before is a meaningless concept.
But, and this is why we're doing this deep dive, that whole idea is crumbling. We're looking at sources from string theory, from loop quantum gravity, that all suggest something else.
That the Big Bang wasn't a beginning at all.
It was a transition, a bridge, a really violent transformative bridge from some earlier era to our own.
And that just changes everything. So today, we're going to dive into the three main contenders for what came before. We're talking colliding parallel universes.
A cosmos that acts like a sponge.
And a universe that, get this, literally forgets how big it is.
And crucially, we're also going to talk about how we might actually test these ideas. This isn't just philosophy anymore. There's a way to look for evidence.
I love that. Okay, so let's start with the first one. To me, this one feels the most cinematic. It says the universe didn't start with a silent expansion from nothing. It started with a clap.
A very, very loud clap. This is the cyclic theory, or as it's sometimes called, the clash of the brains. And to get this, you have to dip your toes into M theory.
Okay, M theory. That's usually where people's eyes glaze over, so break it down for us. What's a brain?
So the theory suggests that our entire universe, everything we can see and touch, is confined to a three-dimensional brain. Think of it like a giant sheet of paper.
Okay, so we're like 2D stick figures living on this piece of paper, and we have no idea there's a whole room around us.
That's a great way to put it. But here's the twist. We're not the only sheet of paper.
There's another one.
There's another brain, a parallel universe separated from ours by a tiny gap in a fourth spatial dimension.
Which is why we can't see it. Light is stuck on our sheet of paper.
Exactly. But gravity isn't. Gravity can leak across that gap, which is part of the theory. But for our story, the important thing is, these brains aren't just sitting there.
They move.
They move. There's a force between them, kind of like a spring, that slowly pulls them together over trillions of years.
And a spring pulls and pulls until...
Collision.
Yeah.
The Big Bang wasn't a moment of creation. It was the physical impact of two three-dimensional worlds smashing into each other.
Wow. Two universes just slapping together.
It's a cataclysmic event. All that kinetic energy from the collision turns into heat and matter. That's what they call the Ekpyrotic phase, from the Greek for conflagration or fire.
So that fire, that's our early universe. The bang is just the sound of the impact.
Metaphorically, yeah. And right after the collision, they bounce apart. The spring stretches, things cool down, galaxies form. That's the phase we're in now. We're expanding.
But that spring is still there.
It's still there, so eventually the force will pull them back together for another collision.
You know, the part of this that I find so elegant is how it deals with dark energy.
Right.
In the standard model, dark energy is this weird, mysterious thing that's making everything fly apart, and we have no idea why.
In the standard model, it's a bug.
Yeah.
In the cyclic theory, it's a feature.
Explain that. Why does this model need dark energy?
Okay, so imagine you want to slam two sheets of paper together. For a clean impact, you need them to be perfectly flat. But what are the wrinkles in a universe? There are galaxies, black holes, all the clumpy stuff. If the brains collided while they were full of that stuff, the new universe would be a total mess.
It wouldn't look like our universe, which is surprisingly smooth on large scales.
Exactly. So you need a cleanup crew. You need something to smooth out the wrinkles before the next collision.
And that's dark energy.
That is dark energy. Its job is to stretch the brain so much that it dilutes everything away, all the matter, all the entropy, until the brain is essentially flat, cold, and empty. It wipes the slate clean.
That's incredible. It gives dark energy a purpose. It's the engine of the cycle.
It is. It's philosophically very satisfying. But let's be honest, it's a heavy lift. It requires extra dimensions, parallel worlds.
Yeah, things we can't prove exist. So what if you're not a fan of extra dimensions?
Well, then let's pivot. Let's talk about a theory that doesn't need any of that. A theory that says the answer is already here, in the fabric of space itself.
This is the sponge theory.
Officially, loop quantum cosmology. And this is the main rival to string theory.
So what's the problem this theory is trying to solve?
It goes right for the throat.
Yeah.
The singularity itself. Einstein's general relativity says gravity always pulls. Always. So if you run time backward, everything must crunch down into a point of infinite density.
And infinite density is just a nice way of saying our math, bro.
Exactly. It's where the theory fails. But then you have quantum mechanics, which says you can't actually pin anything down to a single point. That's the Heisenberg uncertainty principle. Everything's a bit fuzzy.
So you've got Einstein saying it's a point, and quantum mechanics saying, no, it's a fuzzy blob.
A fundamental contradiction. Loop quantum gravity tries to fix this by saying space isn't smooth. It's quantized. It's made of tiny, discrete chunks.
Like pixels on a computer screen. If you zoom in far enough, you see the individual dots.
Perfect analogy. And that leads to the sponge idea. Think of a kitchen sponge. You can soak it with water, right?
Right.
But there's a limit. If you try to squeeze that sponge down to zero size, what happens?
It resists. The material pushes back. You can't do it.
That's what this theory says about space itself. It can only hold so much energy. Once you hit a certain density, the Planck density gravity flips.
Wait, it flips. It becomes repulsor.
It becomes a powerful pushing force. The quantum geometry of space-time itself refuses to be compressed any further.
So instead of a big crunch,
You get a big bounce, the universe contracts, hits that absolute limit, the sponge is fully squeezed, and then violently snaps back out into expansion.
so our ice cream cone is actually an hourglass.
Exactly. We're in the top half, the expanding part.
Yeah.
And before us was a contracting universe that bounced into ours. We're living on the rebound.
And this isn't just a nice idea, right? They've actually modeled this.
They have. People like Apaya Istakar and Martin Bojewald ran the numbers on supercomputers. When they ran the universe backward with these new rules, the singularity it vanished. It got replaced by a quantum bridge.
Wow. Okay, so we've had clapping brains and bouncing sponges,
Yeah.
but you said there was a third option, one that really messes with your head.
It does. This one comes from Sir Roger Penrose, a Nobel laureate who actually worked with Hawking on the original singularity theorems. His idea is called conformal cyclic cosmology.
This is the one where the universe forgets how big it is.
That's the essence of it, yeah.
Yeah.
Penrose starts by looking at the far, far, far future.
The heat death of the universe.
Right. Trillions upon trillions of years from now. All the stars are burnt out, the black holes have evaporated. The universe is just a cold, dark, empty void filled with nothing but photons, particles of light.
Sounds like the end of the story.
You'd think so. But Penrose asks this brilliant question. In a universe where nothing has mass, does scale even exist?
What do you mean?
Well, to measure distance or time, you need a ruler or a clock. And rulers and clocks are made of atoms, things with mass. But photons have no mass. For a photon traveling at the speed of light, time doesn't pass at all.
So if the whole universe is basically just photons,
There's no clock, there's no ruler. The concepts of big and small lose their meaning. The universe literally forgets its own size.
and this is where the Escher art comes in.
Yes, exactly. You know those M.C. Escher prints where he fits an infinite pattern of angels and demons inside a finite circle?
Yeah, it gets smaller and smaller toward the edge.
Penrose says that's what happens to the universe. A universe that is infinitely large and empty is mathematically identical to one that is infinitesimally small and hot.
Hang on, so huge and cold is the same as tiny and hot, as long as you don't have a ruler to tell the difference.
Mathematically, yes. It's a trick called conformal rescaling. The instantly expanded future of one universe just becomes the Big Bang of the next one.
So the heat death isn't an end, it's a reset button.
It's the setup for the next cycle, which he calls an eon. And the craziest part is he thinks this leaves evidence. He predicts that supermassive black hole collisions from the previous eon would send out gravitational waves so powerful they'd punch through the reset and leave faint circular patterns in our sky today.
He's looking for ghosts from a dead universe.
He calls them Hawking points, and people are genuinely looking for them.
Which brings us to, I think, the most important part of this. These are amazing stories. But is this all just a fun story, or can we actually tell which one, if any, is right?
We can, or at least we think we can. There's a potential smoking gun we can look for, and it's called a primordial standard clock.
And we're not talking about finding an actual clock out there.
No. We're talking about very heavy quantum fields that would have existed right at the beginning. These fields would oscillate, like a pendulum. Tick-tock, tick-tock.
Okay, so you have these clocks ticking away in the baby universe.
Now here's the key. While those clocks are ticking, the universe itself is changing size.
Right.
If the universe was expanding exponentially, like in the standard inflation model, that expansion would stretch out the signals from those ticks. It's like the Doppler effect for a siren moving away from you. The pitch drops.
Got it.
But if the universe was contracting before a bounce, like in the cyclic or sponge models, the signal would be squished in a different way.
So by looking at the pattern of these ticks imprinted on the sky, we can tell if the universe was expanding or contracting when they were made.
Precisely. The fingerprint of contraction is different from the fingerprint of inflation. We just have to be able to read it.
Have we found it yet?
Not yet. The signal is incredibly faint, buried in the noise. But the next generation of telescopes are being designed specifically to look for this kind of pattern. We're moving from what if to let's go check.
It's just amazing to think the answer to whether the universe is eternal could be hidden in some static in the sky.
It really reframes our whole existence. I mean, if the standard model is right, we're a one-off, a cosmic accident.
But if any of these cyclic theories are true, then we're part of a continuum. The Big Bang wasn't a moment of creation.
It was a moment of transition, and that leads to some very strange philosophical questions.
You mean eternal recurrence if the universe cycles forever?
Doesn't every possible arrangement of atoms have to happen eventually?
So, is this the first time we've had this conversation?
Or is it the billionth?
And will we have it again?
The physics in some of these models suggests we might.
Wow. I'm gonna need a second to think about that. It turns the cosmos from a straight line into a loop.
A loop? Or maybe a spiral? But definitely not just a simple cone that starts from nothing.
Well, next time you look up at the stars, just remember, you might not be looking at the beginning of everything. You might just be in the middle of a very, very long book.
There's always another chapter.
This has been The Deep Dive. Thanks for joining us for this cycle. We'll see you in the next one.